So in this video, we're going to talk about Newton's work on the binomial theorem. And we've already talked about the theorem. We talked about how Pascal used his triangle to generate the coefficients of the binomials, the binomial expansion. So let's just make a note of that and go over here to the document camera. That when you've got a plus b to the nth power, and n is a whole number, you can use Pascal's triangle to determine the coefficients of the expansion. To determine the coefficients of the expansion. Okay, but what about a plus b to the nth power, where n is a rational number? So Newton answered the question, what if n is any rational number except for 0? Well, yeah, any rational number. Answered the question, what if n is a rational number? So in one of those letters that he wrote to Leibniz, he talks about this. And in this letter in 1676, he shares this in a letter to Leibniz. That P, and this is his notation, P plus PQ raised to the m over n power, if that exponent is a rational number, I can write it in the form of an integer divided by an integer. That's going to equal P to the m over n, that's my leading term, plus m over n times a times q plus m minus n over 2n times bq plus m minus 2n over 3n times CQ plus, and you can guess what the next term is going to be, m minus 3n over 4n times DQ plus ... So in other words, I've got an infinite series here. I've potentially got an infinite series here. And he said that A, B, C, D, and so on, D, and so on, are the preceding terms in the expansion. Okay, so let's expand it. All right, A is the preceding term, which would be P raised to the m over n power. Okay, B, there's B. It's in the third term. It's equal to the second term, but the second term is m over n times A times Q. Well, now I know what A is. A is P to the m over n. So that's m over n times P to the m over n times q. Oops. Okay. So what's C? Well, C is the preceding term, which is m minus n over 2n times bq. And here's B. So this is m minus n over 2n times B, which is m over n times p time to the m over n times q times another q. Okay, that stuff in parentheses right there, that expression in the parentheses is what B is equal to. So when I simplify this, I'm going to rewrite this so that I've got one fraction here. I've got m times m minus n all over 2n times n is 2n squared times p to the m over n times q is q squared. And let's just do one more. What's D? D is the preceding term, which is m minus 2n over 3n times CQ. And now we know what C is. So this is m minus 2n over 3n times. All right, here's the C. M times m minus n all over 2n squared times p to the m over n times q squared. All right, that's what C is. But then I've still got to multiply by q. And let's simplify this, rewrite it so that we've got one fraction out here in front. I'll have m times m minus n times m minus 2n Okay, got it. All over 1 times 2 times 3 times n squared times n is n to the third times p to the m over n times q to the third power. All right, now look at all the places where we've got a 3 in that one for the value of D. Q is raised to the third power. P to the m over n, that doesn't change. That stays constant in every single one of these terms. And then that coefficient out in front, it's a fraction. The numerator has 3 terms in it. The denominator has n to the third in it. Also 1 times 2 times 3, which is 3 factorial. So if I were to take, I could tell you what E is right now. E is going to be m times m minus n times m minus 2n times n minus 3n over 4 factorial times n to the fourth times p to the m over n power times q to the fourth. We've got the pattern. Okay. So let's come over here and let's work with that pattern. I've got p plus pq raised to the m over n power is equal to all of this that I've just been working on. And so let me write it all down. P to the m over n plus, that should be m over n plus m over n times p m over n times q plus m times m minus n all over 2n squared times p to the m over n times q squared plus m times m minus n times m minus 2n, oops, all over 3 factorial, I'm going to write it that way now, 3 factorial n to the third times p to the m over n times q to the third. And I think at that point, we'll just do a dot, dot, dot. You know, the next term is going to be the q to the fourth. You'll have n to the fourth in the denominator, 4 factorial, which is 24. You'll have 4 of these up in the top in the numerator, and so on. Okay, well, let's work on that left-hand side for just a minute. If in the parentheses, I've got a common factor. So I can take P plus PQ to the M over N, and I'm going to factor out a P so that I've got P times 1 plus Q. All of that product is raised to the M over N power, which is P to the M over N times 1 plus Q to the M over N. Oh, well, that kind of makes sense, because that means that when I expand 1 plus Q to the M over N, then every single one of those terms is going to have P to the M over N as a factor. Well, I saw that up here. In other words, I could take the left-hand side of this equation and the right-hand side of this equation and factor out the P to the M over N. Okay. Now, in fact, that's what he does. He takes this, both sides of the equation, and factors out P to the M over N. And he rewrites this. I'm going to write it this way and then write it the way he did it, and just save us a little bit of the algebraic work. All right, so let's take this factored side, P to the M over N times 1 plus Q to the M over N equals P to the M over N times big parentheses. All right, factor P to the M over N out of each one of these terms. I'll have 1 plus M over NQ plus M times M minus N over 2N squared Q squared plus M times M minus N times M minus 2N all over 3 factorial N to the third, that's a factorial, times Q to the third. I'll put it right there, plus dot, 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 close your parentheses. Okay, then what he did was he rewrote each one of these fractions in such a way that he found a different pattern. I'm not real sure why, but he wrote each one of these fractures so that the N squared right there, look at that term right there. N squared's in the denominator. He rewrote this fraction and thought of it as M over N times M minus N over N, all of that divided by 2. So it's sort of like he took the powers of N and distributed them across each one of those factors. And after he does that, this is the pattern that he comes up with. He ends up with P to the M over N times 1 plus M over N over 1 factorial times Q plus M over N times M minus N over N over 2 factorial times Q squared plus M over N times M minus N over N times M minus 2N over N all over 3 factorial times Q to the third plus dot, dot, dot. And then, of course, the next term would be, I'd have 4 of these fractions in the numerator divided by 4 factorial times Q to the fourth. So if he wanted to, so here's an example. X plus Y to the 5/4 power. Here's what he did. Inside those parentheses, he factored out an x and rewrote that as x times 1 plus y over x. All of that is raised to the 5/4 power. Okay, so that's each one of these terms to the 5/4 power. So that's x to the 5/4 times 1 plus y over x to the 5/4. And he uses his binomial theorem, and I'm going to abbreviate that with Newton's NGBT, Newton's generalized binomial theorem on this part. Where m over n, when we compare it to what we've got right here, m over n is 5/4. 1 plus q, q is y over x. Okay. So if I did that, let's just take these first three terms. What I'll end up with is x plus y to the 5/4 power will be x to the 5/4 times 1 plus 5/4 over 1 factorial times y over x to the first power plus 5/4 times times 5 minus 4 over 4 all over 2 factorial times q squared plus 5/4 times 5 minus 4 over 4 times 5 minus 8 over 4 all over 3 factorial times q to the third plus dot, dot, dot. And take a look at this for just a second. I don't have room to write it out, but if we were to simplify all these fractions, I'm going to leave it like here. I just want to point out the pattern here. All right, 5/4 over 1, no big deal. That you just get 5/4 times y over x. But here in the numerator, I've got 5/4 times 1/4. Well, this is 1 1/4 times 1/4. In the next term, I've got 1 1/4 times 1/4 times negative 3/4. And then in the next one, I'll have 1 1/4 times 1/4 times negative 3/4 times negative 1 3/4. What you're doing in that numerator each time is subtracting 1 from the number inside the parentheses. Okay. All right, well, let's try another example. Let us look at, let's let m over n, our exponent, be 3, a positive 3. And let's expand 1 plus q to the third power. Okay, well, when I do that, I would have 1 as my first term plus m over n is 3. So my coefficient is going to be 3 over 1 factorial times q plus my next term is going to be 3 times 2 over 2 factorial. Because remember, I subtracted 1 every time. What I saw from the pattern here is what's happening to those numbers in the numerator is I'm subtracting 1 every time I get a new term. So 3 times 2 factorial times q squared plus 3 times 2 times 1 over 3 factorial times q to the third plus 3 times 2 times 1 times 0 over 4 factorial q to the fourth plus dot, dot, dot. All right, so when we simplify this, what have we got? We've got 1 plus 3 over 1 is 3q plus 6 over 2 is 3q squared plus 6 over 6 is 1 times q to the third is q to the third plus 0 times q to the fourth plus 0 times q to the fifth plus 0 times q to the seventh, fifth, a sixth, and so on and so on and so on. I get a finite series. Well, that's what I would expect. We've always raised something to the third power and we've gotten 4 terms. So Newton's theorem is going to work, and it's a good thing it does. Otherwise, it's not much use to us. Newton's theorem pulls through for us even when m over n is a rational number, which is also a natural number. Okay, we don't get an infinite series because out here we're adding zeros. Okay, so we've got this finite series with 4 terms. Okay, let's try another number. What about the square root of a number? So the square root of 1 plus q is 1 plus q to the 1/2 power. And in this case, my exponent is 1/2. So using Newton's notation, m over n would be 1/2. And when I would expand this, I would get 1 plus 1/2 over 1 factorial times q to the first power plus 1/2 times negative 1/2 over 2 factorial times q squared plus, keep subtracting 1/2 times negative 1/2 times negative 3/2 over 3 factorial times q factorial. I'm sorry, times q to the third plus dot, dot, dot. And when I come back and I simplify my fractions, I'll get, I've already done this, I get 1 plus 1/2 q minus 1/8 q squared plus 1/16 q to the third minus 5 over 128 q to the fourth plus dot, dot, dot. I get an alternating series. Plus, minus, plus, minus. All right, well, let's substitute in a number here. Let's substitute in, let's let q equal 1/2. And what we're trying to get is the square root of 1 plus 1/2, which is the square root of 1.5. We get 1 plus 1/2 times 1/2 minus 1/8 times 1/2 to the second power plus 1/16 times 1/2 to the third minus 5 over 128 times 1/2 to the fourth plus dot, dot, dot. And I've done the arithmetic. That's 1 plus a fourth minus 1 over 32 plus 1 over 128 minus 5 over 2048 And if I look at the series, the sequence of partial terms, partial sums, sequence of partial sums, I get 1.25, add the first three numbers, 1.21875, add the first four, 1.2265625, and then 1.224121094, and then just keep going. And so if I compare that to what I get with my calculator, the square root of 1.5 is about 1.224744871. So using Newton's method, I've got it to the nearest. I'd have to go out one more place probably to get it to know definitely that I would need to round up to 0.225. Okay. So think about this for a minute. This is going to allow him to work with, I mean, just doing this much has introduced the whole topic of infinite series. You've got to talk about convergence. You've got finite series, infinite series. You've got alternating series, all kinds of stuff going on here. How many times do I have to, how far out do I have to go to get the accuracy that I want? What if I use a negative number as my exponent? Well, that would work. This is not restricted to positive numbers. I could use a negative number. All right. What about the square root of 7? Well, if we follow the strategy that we've been using, I would write the square root of 7 as the square root of 1 plus 6, and I would let q equal 6 and m is 1/2. And when I substitute those in there, I'd get this is equal to 1 plus 1/2 times 6, 1/2 times q, minus 1/8 times 6 squared. Actually, what I did was go back to here, and I'm just substituting 6 in for q, because this is something to the 1/2 power. So I'm substituting 6 in here for q, plus 1/16 times 6 to the third minus 5 over 128 times 6 to the fourth plus ... And that gives me 1 plus 3 minus 36 over 8 plus 216 over 6 minus 5 times 1,296 over 128. All right, y'all can catch up with those fractions. Put it on pause if you need to. And then look at your partial sums. Well, this is odd. I get 1, and then 1 plus 3 is 4. And then 4 minus 4.5, I get -0.5. And then -4.5 plus 30 something, I get 13. Does that sound right? 1 plus 3. Let's see, I don't have a calculator with me. Yes, I do. Well, hold on. So when I add the first 4 terms, add 216 over 6 to -1/2, I get 35.5. And then that number minus 5 times 1,296 divided by 128, I get -15.125. This is not a convergent sequence. This is in no way getting closer and closer to the square root of 7. not a convergent sequence, getting closer to the square root of 7. All right, let me show you how to fix it, and then I'll tell you why. All right, so Newton said we need to use a little bit of a trick here. I'm going to take the square root of 7, and I'm going to rewrite that as the square root of 9 times 7 ninths. 9 times 7 ninths is the same thing as 7. And this is the same thing as the square root of 9 times the square root of 7 ninths, which is 3 times the square root of 1 minus 2 ninths. And now what I'm going to do is expand the square root of 1 minus 2 ninths and let Q be negative 2 ninths. And my M over N is 1/2. And so when I do that, I'm going to get 1 plus 1/2 times negative 2 ninths minus an 8 times negative 2 ninths squared plus 1/16 times negative 2 ninths to the third minus 5 over 128 times negative 2 ninths to the fourth. And you know, I'm feeling better about this already because I know that when I'm multiplying by a fraction, multiplying by a number between -1 and 1, the absolute value of this number is getting closer and closer to 0. That was certainly not happening up here. Okay, so I'm feeling better about this already. And when I do the arithmetic, I get 1 minus a ninth minus 4 over 648 minus 8 over 11,664 minus 80,000 over 839,808 minus ... Now notice this one's not an alternating series. So this is going to converge from one side. My partial sums are 1, and I'm just going to round off to 4 decimal places, 0.8889, 0.8827, 0.8820, 0.8819, and so on. But don't forget, we've got to multiply by 3. The square root of 7 is equal to 3 times the square root of 7 ninths. And so that's pretty close to 3 times 0.8819, which is 2.6457. And if I use my calculator, I'll get the square root of 7. If I round it off to 4 decimal places, I'll get 2.6458. Real close. Okay. So pause this if you need to catch up with the arithmetic, but I'm going to keep going and write one more thing, because what that leads us to is that eventually somebody said, you know, Newton's really close, but at the time of Newton, we didn't have the rigor that we do in mathematics today. And so today, what I need to do is I'm going to be able to generalize it some more, but I'm also going to put a restriction on this process. So today, the generalized binomial theorem. This is not the Newton one, but the all-time general binomial theorem, generalized, says if alpha is a real number, x is a real number, and the absolute value of x is less than 1, then 1 plus x to the alpha, and see how that notation is coming from what Newton did. He used M over N, not an alpha, but he was talking about rational numbers. And now we have restricted it. So this number I'm adding to 1 has to be between -1 and +1. If it's bigger than 1, I'm going to have to make that use that little trick that I did over there with the square root of 9. This is equal to 1 plus alpha x. By now you could probably write it down. Plus alpha times alpha minus 1 over 2 factorial times x squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial x to the third plus ... That, my friends, is the end of the story for the generalized binomial theorem. But look at what Newton did, wanting to take that binomial theorem where the exponent was a natural number, taking that and expanding it, making it more general so that the exponent could be any rational number. Look at all the mathematics that has led to. That's pretty amazing. All right.